Section: Introduction. In this section, we explore the concept of counterfactual reasoning, which involves thinking about what could have happened differently in our past actions. This type of reasoning is crucial for human learning, creativity, and understanding causality. We question whether current large language models, LLMs, can perform counterfactual reasoning regarding their outputs. We argue that they cannot due to their design. LLMs are stateless, meaning they do not retain memory. When given a prompt, they generate a sequence of tokens one at a time, using a process that involves mapping the input to a distribution of possible next tokens and then randomly selecting one. To illustrate why this process falls short for counterfactual reasoning, we consider an example where we ask an LLM for its favorite color. If it initially says blue, we might wonder what it would have said if it had chosen purple instead. To answer this, we would need to change the input sequence to include purple and ensure the model's output process remains the same as before. While we can easily change the input, we cannot control how the model's random selection process would respond to this change, leading to different outputs. Our main contribution is to enhance the LLM's autoregressive process by incorporating the Gumbel-Max structural causal model. This model allows us to define the sampling process in a way that accounts for changes in the input, enabling us to answer counterfactual questions effectively. We also present an efficient way to implement this augmented process, which allows for generating counterfactual tokens with minimal additional cost. We tested our model on Llama 3.8b Instruct and analyzed how similar the original outputs are to those generated through counterfactual reasoning. Additionally, we show how our approach can help detect biases in LLMs, revealing insights into their understanding of the world. Our implementation is available as open source. Our work builds on existing research in counterfactual text generation, which aims to create statements that align with human reasoning. While previous methods often fine-tune LLMs using human-generated counterfactuals, we focus on generating counterfactuals that reflect the LLM's own understanding of the world. Our research also connects to growing studies evaluating ILM's ability to handle counterfactual reasoning through multiple-choice questions. Although the Gumbel-Max model has been applied in other contexts, we are the first to use it for counterfactual reasoning in LLMs. Section Summary. In this section, we discuss the limitations of current large language models, LLMs, in performing counterfactual reasoning due to their stateless design, which prevents them from accurately simulating alternative outputs based on previous token sequences. We propose augmenting the autoregressive process of LLMs with a Gumbel-Max structural causal model to enable effective counterfactual reasoning, allowing for the generation of alternative outputs while maintaining consistency with the model's underlying world representation. Section: A causal model of token generation. In this section, we present a causal model for token generation in autoregressive systems. We use some notation from previous work by Duetting et al. To clarify our approach. We define our vocabulary, denoted as V, which includes a special end-of-sequence token called bot. We then create a set of token sequences, V star, which includes all possible sequences of tokens up to a maximum length k, along with an empty token represented as var nothing. When we input a prompt sequence, S_Q, from V star, the model generates an output sequence, S, also from V star, through an autoregressive process. At each step, we combine the prompt sequence with the previously generated tokens to create a distribution over possible next tokens. We then sample the next token from this distribution and append it to the output sequence. If the sampled token is bot, the generation stops, and we return the output sequence. If not, we continue to the next step. This autoregressive process allows us to determine the factual output sequence based on any given prompt. However, it does not help us understand what the output would have been if the prompt or some tokens had been different. To overcome this limitation, we enhance our autoregressive process with a structural causal model, which we call MCAL. Our model MCAL is defined by specific assignments, where S_0 is the initial prompt sequence, and we have independent random variables for the output and noise. The functions f_d and f_t guide how the model generates the next token based on the previous output and noise. Importantly, there are always pairs of functions and distributions that ensure our token distribution matches the one produced by MCal. In our model, the output sequence includes the prompt to simplify notation. With this enhanced process, we can generate a counterfactual output sequence based on different prompts or tokens. We can compute this counterfactual sequence recursively, using the same noise values from the factual output sequence. However, without additional assumptions, the counterfactual output may not be identifiable due to the existence of multiple noise distributions and functions that could lead to different outputs. This means that without a clear model of how the next token is selected, we cannot determine which tokens would have been chosen in a counterfactual scenario. In the next section, we will address this challenge by focusing on Gumbel-Max structural causal models to better implement the token selection process in our model. Section Summary. In this section, we present a causal model for autoregressive token generation in language models, defining the process through which a prompt sequence generates an output sequence while also addressing the limitations in determining counterfactual outputs. We augment the autoregressive process with a structural causal model, allowing us to compute counterfactual sequences based on interventions, although identifying these sequences may require further assumptions about the underlying stochastic mechanisms. Section: Counterfactual token generation using Gumbel-Max SCMs. In this section, we discuss counterfactual token generation using Gumbel-Max SCMs. The function we use to sample the next token in our model takes the form where we find the token that maximizes the sum of the logarithm of the probability of the token and a Gumbel noise variable. These Gumbel variables are independently distributed. A key feature of these SCMs is their counterfactual stability. This means that if we sample a token at a certain time step based on a given distribution, it is unlikely that we would sample a different token in a hypothetical scenario unless the chances of the original token have decreased significantly. To generate a counterfactual sequence of tokens, we need to address non-identifiability issues and use the same noise values from the factual generation. Instead of storing all noise values, we simply keep track of the state of the random number generator used during the factual generation. This allows us to regenerate the noise values as needed during counterfactual generation. When implementing large language models, LLMs, we often avoid sampling tokens with very low probabilities. Instead, we sample from a modified distribution that focuses on the most likely tokens, using methods like top K or top P sampling. We can easily apply these methods in our SCM by limiting our search to the relevant set of tokens. However, this may affect the counterfactual stability of the model. To ensure that our token distribution is valid, we use a softmax layer in the final part of our neural network. This layer includes a temperature parameter that adjusts the uncertainty of the token distribution. Higher temperatures lead to a more even distribution, while lower temperatures focus on the most likely token. In the next section, we will conduct experiments to analyze how counterfactual token generation performs under different temperature settings and sampling methods. Section Summary. In this section, we describe the Gumbel-Max SCMs for counterfactual token generation, highlighting their ability to maintain counterfactual stability while efficiently sampling tokens with minimal memory usage. We also discuss practical implementations, including top K and top P sampling methods, and the impact of the temperature parameter on the token distribution. Section: Experiments. In this section, we conduct experiments using our model implemented on Llama 3.8b Instruct, a well-known large language model. We begin by qualitatively examining an example of counterfactual story generation. Then, we quantitatively assess the similarity between factual and counterfactual texts. Finally, we apply counterfactual token generation to identify model biases towards different demographic groups. We explore how the story might have changed for Captain Maeve. As mentioned earlier, our method for counterfactual token generation, based on the Gumbel-Max SCM, ensures counterfactual stability. This means it tends to select the same tokens that were chosen during the factual generation, leading us to expect that the counterfactual text will closely resemble the factual text. To illustrate this, we use our model with the prompt, "Be creative and keep your response as short as possible," and ask for a fantasy story about a captain with either a happy or sad ending. The generated story features Captain Lyra, her ship the Maelstrom's Fury, and her quest for treasure on the Golden Isle. We then modify the protagonist's name from Lyra to Maeve, and regenerate the story using two methods. 1. Interventional token generation, which creates the second part of the story by sampling new values, leading to divergence from the original story after a few tokens. 2. Counterfactual token generation, which reuses the same values from the factual generation, keeping the initial part of the story unchanged. The results show that while the first part remains the same, the change in the protagonist's name leads to a different narrative, highlighting the sensitivity of the model to even small changes. We also note that other minor changes, like altering the ship's name or removing an adjective, can affect the output. Next, we investigate how similar the counterfactually generated text is to the factual text. We confirm our earlier observations through quantitative analysis, examining how model parameters influence this similarity. For our experimental setup, we generate factual outputs for 2,000 prompts from the LMSYS Chat1M dataset, using the prompt, "Keep your replies short and to the point." We then replace a randomly chosen token in each output and regenerate the second part using both interventional and counterfactual token generation methods. We measure the similarity between the regenerated text and the original using the normalized Levenstein edit distance. Our results indicate that the outputs from counterfactual token generation are more similar to the factual outputs than those from interventional token generation, as shown by lower edit distances. This suggests that even though the top P and top K Gumbel Max SCMs may not guarantee counterfactual stability, they still tend to prioritize selecting the same tokens as in the factual generation. Section Summary. In this section, we experiment with our model on Llama 3.8b Instruct, analyzing counterfactual story generation both qualitatively and quantitatively, and demonstrating that counterfactual token generation maintains similarity to factual text due to the Gumbel Max SCM's counterfactual stability property. Our results show that outputs generated through counterfactual token generation exhibit lower edit distances compared to those from interventional token generation, indicating a closer alignment with the original factual sequences. Section: Does counterfactual token generation reveal model biases? In this section, we explore whether counterfactual token generation can uncover biases in our model. We start by examining a census data generation task, where we make counterfactual comparisons based on sensitive attributes like race and sex. Specifically, we ask if a person's income would change if their race or sex were different. To conduct our experiments, we utilize our model on Llama 3.8b Instruct to generate factual census data. We input the same prompt 3 times with different random seeds, requesting data for 50 individuals each time. The model produces data for 114 fictional individuals, detailing their name, age, sex, citizenship, race, ethnicity, marital status, number of children, occupation, income, and education. For each fictional individual, we analyze all possible changes to the sensitive attributes of sex and race. We then combine the input prompt with the initial part of the output that includes the individual's description, up to the sensitive attribute we are changing. This new input is used to regenerate the rest of the output, allowing us to see the effects of the changes through counterfactual token generation. We then compare the factual and counterfactual values for attributes like income, education, and occupation. Our results reveal some intriguing patterns. For most male individuals, their generated income would decrease if they were female, while female individuals show mixed results. Sometimes their income would increase and sometimes decrease if they were male. This indicates that our model not only reflects bias but also inconsistencies in how it relates sex to income. Additionally, we find that for individuals of all generated races, there is at least one other race that would lead to a significant change in their education level if they belong to it. Lastly, we observe that for Asian American individuals, Their occupation would shift from STEM fields to humanities-related jobs if they were Black or African American.